Hi guys, welcome to this very interesting web series which is on machine learning fundamentals. We were on episode 6 last time, and this is episode 7 of this particular series, which will be on a very interesting subtopic in machine learning. In supervised learning, we'll be going to decision trees. Uh, we have taken supervised learning, logistic regression, and in fact, in unsupervised also we had taken the basic thing, which was k-means and PCA, and we had taken linear regression and logistic regression as far as supervised learning is concerned. But this is the proper time when other algorithms which are there in supervised learning, they should be introduced to you, and from here then we will be taking next few more algorithms to understand supervised and in fact some of the advanced algorithms in supervised and unsupervised learning before we can go to reinforcement learning. So here we go. Without any further delay, let me just go directly to the slides first of all, and I'll wrap them fast, and then after that I'll be showing you a use case of this decision tree. In fact, one of the common examples we had been taking, in fact, in the uh, previous segments as well. We have taken the example of student performance. So with that, I'll be showcasing you this implementation as well in Python. And this is in fact, understanding the power of trees. Uh, this is a tree-based machine learning algorithm. So decision tree. What is a decision tree? A decision tree is a supervised learning algorithm. It is used for both classification and regression. If you remember, we had taken earlier. So this is that. That's the reason this was the perfect time that to take a decision tree, because in supervised learning earlier we had taken both logistic regression, in fact, and in fact linear regression. So classification, regression, in fact, both can be it can be both done. So it uses a tree-like structure. So it will be having a logic tree. In fact, we'll be going deep diving into that. The example is given, in fact, there, but we'll just take a much deeper look into what exactly this tree is, and it will be having a tree structure where internal nodes represent conditions or tests on features. So the nodes which are there internal, they are representing the conditions that are, or the tests that will be applied on the features, branches, represent the outcomes of those tests, and definitely then branches are representing what are the outcomes of that. It will be much more clear with the diagram which is shown next as an example. So there are root nodes in this, the initial nodes. So I'll be showcasing you that as well. And then there are leaf nodes that are containing the final decision or the predictions which are there. The algorithm is it works recursively, and it goes on splitting, dividing the data into increasingly homogeneous subsets until reaching a pure node. That means where there is no ambiguity. It's a pure node. There is no ambiguity whatsoever. There are not multiple answers, and then or the stopping criteria is there. So one of these conditions should be met so that we can stop. Uh, so this is what decision tree is, and it's a supervised learning algorithm. But if there is any doubt whatsoever, so that we can clarify with the diagram or the example which is shown here. We have seen what decision tree is. So it is in fact a logical structure, a tree structure which is there using decision trees for classification. So we are using decision trees here for classification. So example which can be there for the classification is value for a feature specified. Move along the edge labeled with this value. If you reach a leaf, return the leaf of the leaf. Okay, label of the leaf, and otherwise you repeat step 1. So it will be until it reaches to a leaf, it will be returning. Otherwise it will be returning from, it will be repeating the step 1 again. So what does that mean? Here we are trying to do one thing. We are deciding the weather, if it is a appropriate weather, feasible weather conditions are there to go on a picnic, or there is, or playing, for example, or no playing, or picnic, going for a picnic or not going for a picnic. So this is, what we can take. We can use decision trees for that. So we are starting with this root node outlook, and then there can be three, in fact, categories in this classifications. One will be that it is sunny. One more condition will be that it is overcast, or it can be a rainy condition. So these three. Now, if it is sunny, the decision tree is reaching the. If it is sunny, so what is humidity? So if humidity is high, then we don't want to go. No picnic or no play. If the humidity is normal, so we'll go for picnic, or we'll go for playing. If outlook is overcast, then without any further conditions, there is no further condition, we are going for picnic or we are going for playing. And then there is one more, rain. If it's rainy, and then again with rain it is windy as well. If it is true, then there is no play. If it is rain, and then there is no wind, there is play or there is picnic, in that particular condition. So these are, this is, this is an I would say an appropriate example, which, with which decision trees can do the classification, and we are reaching to conclusion. These nodes which you see where N and P is written, these are the leaf nodes, which are giving us the ultimate decision. So that is exactly what was reiterated, what was in fact stated here, that leaf nodes, the leaf nodes contain the final prediction. So they are the nodes which are containing the final prediction, and in fact, they are giving us the exact idea of, or the decision which is there. This is the these are the basics of decision, what decision tree is. And there are several advantages, in fact, when we are comparing decision trees with what we were having earlier. What we are getting is decision trees are offering several compelling advantages that are making them preferred choice in machine learning. So there are numerous advantages that these decision trees are having, and in fact, that is these are the preferred choice in machine learning. So their intuitive structure mirrors human reasoning, making them accessible to both technical and non-technical stakeholders in artificial intelligence and cybersecurity applications or other applications which are there. So what are the key advantages that decision trees are having? First one is high interpretability. The rule-based decisions are easy to understand and explain. So their interpretability is very, it's excellent. Interpretability is something to do with the way, the logic with which a particular decision is reached. So if that is there, I think decision trees are providing that optimal level of, or appropriate level of, logic to understand that, why this decision has been taken, which might be missing, or there might be some ambiguity, whereas comparison with others are concerned. We'll be seeing that comparison as well. Versatility, data handling. So versatility in handling the data. It handles both numerical as well as categorical data seamlessly. So this is one more advantage that these decision trees are having. Minimal pre-processing. So you don't need to pre-process. No feature scaling or normalization is required in the data. You can just take the data and directly fed it, and decision trees will be taking care of it. Non-linear captures complex non-linear relationships effectively. So this is one more aspect where you are having, complex relationships which are non-linear in nature. They can be they can be captured by decision trees very easily. What is the algorithm process? Select the best feature for splitting the data. So it will be selecting the best feature so that it can split the data. Divide the data set into subsets based on feature values. Repeat the splitting if it is required. Otherwise, if it is reaching to a particular leaf node where a decision is there, stops when nodes are pure or maximum depth. So maximum depth we are in fact specifying. We can give, for example, depth 4. So it will be going to 4 steps, so that we can see in the practical example there where the implementation comes in Python. So that is in fact we are going to do. Uh, Goal, create homogeneous data sets where each group, so it's creating homogeneous data sets where each group contains similar outcomes. So this is how the algorithm decision tree works. And as far as the visual understanding of components is concerned, decision tree consists of 4 key structural components. So we need to remember this. Uh, these are working together to make predictions. Understanding these components, as I'm saying that it's very critical. Understanding these components help us visualize how the algorithm processes the data and the input to final decision output. So what exactly the decision tree is doing, visual understanding of the components is something very important to comprehend what happens exactly, how the algorithm processes the data, uh, uh, you know, from input to output decision, from input to final decision output. So how it is being processed, it is very important to understand these components. Root node, a straight point where the first decision is made. So we had in fact shown it earlier as well with the earlier example. Then internal nodes, decision points that test conditions on features. So they are testing the conditions on the features, whether which condition is true. And branches are their connections representing decision outcomes. So these are representing the decision outcomes. We can just correlate these components to the earlier example as well. And the leaf nodes are the terminal nodes which are containing the final predictions. As in our case, in the earlier case, we were having these ands and p's which are there. So these are the leaf nodes. And then, for example, from outlook to humidity and windy, these are the nodes which are you know which are internal nodes, decision points that test the conditions. No, these are the branches, and if you just see, these are the branches, and then these conditions which are in between, which are connecting these are called as internal nodes, decision points that test condition on features. So on the features that is testing the condition, so these are internal nodes. So we can correlate it to any example for that matter, not the one which was previously given there. That was very simple example. We can have very complicated decision tree structure as well, but you can just compare these components visual for understanding. This is very important to understand the logic of decision trees. And then there are in fact concepts. One of these concepts I am just opening up fully in this particular video, and then next, because I am just using this in one of the practical implementations. I am using that. So I will be in fact opening this Gini impurity, entropy and information gain. In fact, I'll be giving the brief of all 3 of them, but I will open up Gini impurity today, and I will be giving a detailed explanation of this before I can just go and show you the program which is written in using decision trees. Gini impurity is it measures the likelihood of misclassification. So it is measuring the likelihood. What is the likelihood what is the possibility of misclassification if a randomly chosen element were labeled according to the distribution in the subset. I will just open it fully and you will understand this with an example. Next slide which is coming. So it is giving that how this Gini impurity is calculated. Entropy, in fact, not in today's this one, but we can just say it quantifies the disorder of randomness in a data. Higher entropy means the more mixed class. If it is more mixed class, it is higher entropy. That means disorder or randomness is more. So this is used to quantify, and then definitely information gain is connected to entropy. The reduction in entropy achieved after splitting on a feature algorithm selects the feature that maximizes this gain. So information gain will be choosing, it's a logic where maximum information gain has happened, it will be choosing that feature. So reduction in entropy achieved after splitting on a feature is what information gain is. The algorithm evaluates each feature and chooses the one that maximizes purity improvements in resulting subsets. So definitely because what we intend that we should be having maximum purity achieved. Now this will be much more clear when we are first of all giving what is Gini impurity. So as far as the definition is concerned, we have already seen it, but one line definition can be Gini impurity measures how mixed the classes are in a node. If it is a fully mixed class, that means there is more impurity. If it is, for example, in case of a student's performance, if we are splitting the data and I am getting pass, 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 that means all the three instances which are there, they are pass. That means data is pure. That means data is pure, and then definitely the Gini impurity which is there, that will be zero. So if the Gini impurity is zero, means perfectly, it's a perfect purity, and we can go ahead. So this is a perfect purity, and if for example it is a 1, that means there is maximum impurity, or it is a mixed class, it's a random class which is there. So if I randomly pick one sample from this node, how likely it is that I would classify it incorrectly if I labeled it randomly according to class distribution. That is what Gini impurity is. If I am randomly picking one sample from this node, so how likely is it that I would classify it incorrectly if I labeled it randomly according to the class distribution. So what is the formula for calculating this for a node? So for example, a node with classes 1, 2, so on up till n, Gini impurity is equivalent to 1 minus summation of pi square. So what does that mean? Pi raised to power 2, summation of pi. That means as many as occurrences are there. So as many as occurrences are there, it will be a summation plus of those. That means Gini will be equivalent to 1 minus p1 square plus p2 square. So if we, for example, put it into an example, now we are taking case 1. Case 1 is a first example, pure node. Suppose all students are passed. So that means P pass is equal to 1, P fail is equal to 0. There are two probabilities. Classifications are there, pass or fail. Now all students are pass. That means pass is equal to 1, P pass is equal to 1, P fail is 0. So how we have to calculate Gini impurity on this. Gini is equal to 1 minus 1 square. That means pass, the value of pass P1 is 1 square. The value of fail is 0 square. It will be 1 minus 1 Gini is equal to 0. So it means that this is perfect purity. So this is a perfect purity, and we have got the result as 0 for Gini impurity. Now there can be one more case in which mixed nodes can be there. Suppose a node has 5 pass, 5 fail. 5 students are having pass and 5 students are fail. So P pass is equal to 0.5, definitely half of them. P fail is equal to 0.5, again half of them. So what will be the value of Gini? It's going to be 1 minus as it is displayed on the screen. 1 minus 0.5 square plus 0.5 square, it will be 1 minus 0.25 plus 0.25. The Gini is equivalent to 0.5. This is highly impure, because exactly half of it is getting half, meaning lower Gini, better purity. If it is lower Gini, it is better purity. Higher Gini, more mixing. The tree chooses the supplet that gives the lowest weighted Gini after suppleting. So it is choosing that supplet which will be giving it the lowest weighted Gini after suppleting. So this is how we calculate the Gini. Then I'll just tell you, a Gini impurity, how it is used in, for example, in this case, where we are having this student prediction. So first of all, let me just go to this directly here. I am trying to just show you the Python program in which we are having. I wanted to show you the data as well. I don't think, okay, this is not the one. Okay, let me just show you the file which is there. I am having one student performance. Yeah, so this is the file. I will just display it. So this should be with you. These are five. If you just see these, there are five parameters in this one. Five. There are, yeah. Oh no. 1, 2, 3, 4, 5, 6, 7 features are there. 7 features are there in this particular file, starting with study hours. So we have taken this example multiple times. It might be a little more complicated data, but it's same. Student attendance or study hours is there, sorry, and then attendance is there. Assignment score is there, and then midterm marks, lab performance, and what are the marks in that, previous grades which are there, and then the results, previous results which are there. For these, now these are the results which are there. So this is the data which goes, and I will close it, so I don't need to save it anyways. And then you can just see this program which is in front of you now. We are not doing anything new, just applying into it the decision tree and how that is done. We are having, so this is all import. We are importing pandas, matplotlib for plotting, and then we are having the decision tree classifier and the plot tree, which is there from sklearn. And then again, the train test split we are importing. This is not for the first time we are doing it. And from sklearn itself, we are importing accuracy score, classification report, and confusion matrix probably for the first time. But this is again, we are putting confusion matrix in this so that it gives us clearer. But one thing is there, confusion matrix, as far as talking about confusion matrix is concerned, we have just done, in one of the examples, I had given the explanation of that as well, but not to such an extent. But in the next episode probably, because we'll be going through now the advanced algorithms as well. So where we'll be commonly generating this confusion matrix to understand things in a better manner. So it will be definitely a clearer view of this will be given. What we are doing, this is a simple thing where we are taking the data. We are reading it from a student performance.csv that I have saved in the same folder where this program exists. Mind you, that is something very important, or else you need to give the exact path here in this line where you are. So if it is on your C drive or a D drive, some folder is there, you have to give the exact path here in case it is not in the folder where your program is. So there are two ways in which it can be done. And then again, x is equal to df, and then we are putting all these features which are there: study hours, attendance, assignment score, midterm marks, lab performance, previous grades, and then we are having the results. That will be something which will be predicted. So we are putting these to the x, all those features, and then the last one, which is the results that we are putting in. That's what we are expecting outcome prediction on that. And then x underscore train and all of these, we train test split, we are putting that there. This is not for the first time we are doing it. X comma y test underscore size is equal to, we are putting 30% of the data as test and 70% as train. And random state, not for the first time, we want to just get consistency in the results. So that is how it is completely, here you can just say by convention we are using 42. So I had given an explanation in the earlier videos as well, detailed for this random state. And this is not for the first time we are using it. Model is equal to decision tree class for now here. There are a few things which are new. So first of all, criterion. We can use multiple criterias as we have mentioned. We can use this criteria which is which is a Gini. So Gini impurity can be used, or we can have in fact the entropy as well used. So now in this case, I'm not going to entropy at all because we have not, in a deeper manner, we have not understood the entropy, how that is calculated. I'll be showing that separately. So here we are using a criterion which is Gini impurity, and that you have already seen how it is calculated. And max underscore depth is equal to 4. That means how many maximum depth of a decision tree is going to be 4. We are deciding it. And random state 42, again, I don't need to explain that. Then we are putting this into a model. Model.fit is equal to x underscore train and y underscore train. This is not for the first time. Y underscore prediction is equal to model.predict x underscore test. And then we are printing accuracy. We are printing the classification report, and then confusion matrix. So all of that we are printing, and then in fact we are predicting now the scores of a new student who is given on this new underscore student is equal to these are the study hours and marks and rest of the things, previous performance percentage, and this is what we are putting, and we'll be getting prediction for this particular student, right? We are saying model.predict student new underscore student, so new student is this one, and it will be predicting. After predicting, it will plot a graph, in fact tree first of all for this. So it will be giving we are putting a fixed size plot tree, model, feature name, x dot column, class name, model dot classes. So this is the main thing which is there for plotting the graph. Not necessary for the program or logic to understand, but this is just giving us a visual understanding. And then filled is equal to true, rounded is equal to true, font size is equal to 10. So that is the font, and plot the title is equal to decision tree for student performance prediction, and it will be showing with this plot.show. If I'm running this program, you can just see first of all the results here. Then it will be giving this tree as well. It will give confusion matrix. Yeah, I want to just utilize the maximum portion of this screen so that you can understand it better. So let me just go to run and run without debugging. If you just see the program is running, and it will be giving us the output. First of all, the accuracy. So let me just leave it for the moment. This decision tree which is there. So actually this is the main output of the program which we were in fact expecting. So accuracy is 1, and classification report, it is saying precision is 1, recall it's 1, F1 score is 1, support 3. I know that all of these things you'll not be able to understand. We have not explained this yet completely. So this precision, recall, F1 score, and support, all of these things I'm going to take in fact in the next episode first, and that will be followed by the example in Python again. So accuracy, it is just giving and then confusion matrix. If you see, we had seen it already. Confusion matrix, we have done the interpreting little bit of that. So if you just see it's saying 3003, that means it's 100% giving us the results. So when it comes to this true negatives, it is 3 out of 3. True positives, it's 3 out of 3. So that this is what this confusion matrix is saying. And then the prediction for new student is passed with those parameters which were given here. So student is having these parameters which are here in this line, and for this student we are getting the prediction as pass. If you just see this decision tree, now I am going to just showcase this. So if you see this decision tree which is there, now decision tree for student performance, this is what we had built. And in fact, lab performance less than or equal to 64, Gini is equal to 0.49. It's calculating all these things, samples 14, value 6, 8, class is pass. So you can just see this, this decision tree which is there, and how it has reached samples 6, value 6, class fail. So Gini is equal to 0, samples 8, value 0, 0 and a class is equal to pass. So this is, how it has reached to this conclusion. So this is how this, this particular program is working, and it is providing us the results. So this is, this is it for this particular episode 7, which was on again the supervised learning. But we have taken a very important concept today, which was of decision trees. Decision trees, in my opinion, has it forms the foundation of, as far as the supervised learning, complex implementation of supervised learning is concerned. It forms the basics of first, and gives a way to other algorithms. For example, random forest and others to for somebody who is new into it to understand. So you should be having a clear idea of this. Now, with this example which we have given here, implementing decision trees, you can just try this decision tree on some other example. It can be applied to numerous other examples as well, and that will be giving you a good confidence in this. And hope that this particular video on decision trees, supervised learning, again, it would have been very beneficial to you. And I look forward to have you again in the next episode, which will be in episode 8. It will be for one more important algorithm in supervised learning, and it will be giving you deeper insights into few more concepts. For example, entropy and information gain, and what is the relationship there, and deeper understanding of those concepts with the formulas, and how they are how the entropy is calculated, like we had done it for the Gini impurity. So see you then. You can subscribe this channel. Whenever a video gets uploaded, you will be informed about that. If you feel that this particular channel is informative for you, please subscribe, and provide us your valuable feedback, so that we can improve our next for our next series, or for the videos which we are going to, in fact, develop and publish for this particular series. Thank you once again for connecting.